Have you ever found yourself lost in the sea of colorful beads trying to create the perfect ornament? What if I told you there is a mad person hidden behind those beads? Can teach us combinations and patterns. Today we are diving into the fascinating world of bead ornaments where creativity meets logic. Let's unravel the mystery together. Alright, let's dive into the fascinating world of bead ornaments. We'll unpack the logic behind this solution step by step, ensuring we understand the underlying principle before we get into coding details. First off, the problem we are tackling involves getting the number of unique ways to arrange bits on a string when each type of bit can have a different quantity. It's a combination challenge, and to solve it effectively, we need to leverage some mathematical principles, particularly those involving modular arithmetic. Checkpoint 1, understanding modular arithmetic. So we are working with very large numbers here, especially when we start calculating combinations. That's where the constant value mod, which is set to 1 billion plus 7, comes into play. This is a common modulus used in competitive programming to avoid overflow and ensures that our results fit within the standard data types. Checkpoint 2, modular exponential. Now, before we dive into the main solution, let's talk about the ModPow function. This utility is crucial because it allows us to calculate powers of numbers while keeping everything within the bounds set by mod. Where we need, why do we need this? Imagine you have a bit type with a large number, say a million, and if you want to compute a value like this that can get astronomically large, like very quickly, the mod power function uses an efficient method called exponentiation by squaring, which lets us calculate these large powers in algorithmic time. This is a game changer when it comes to performance. Checkpoint 3, the main logic of bit ornaments is like next. Let's look the bits ornament solution function. Here's where things get interesting, where we kick off by determining the total number of bits we have and results, and setting our results to one that will hold the final count of arrangements. As we loop through each bit type in the list, we calculate the total number of arrangements for the type. For each bit type, we apply our mod power function to compute the bits. The reason we do this is rooted in the combination mathematics. When arranging items in a circular fashion, the number of distinct arrangements is given by this formula. By multiplying this result into our result variable, we are progressively building up the total number of unique arrangements from each bit type. Alright, checkpoint 4, accounting for total bits and types. After processing each individual bit type, we need to account for the total arrangement considering the distinct types we have. Here we perform another mod power calculation, this time using the total number of bits and reducing the exponent by 2, which relates back to how we calculate for indistinguishable arrangements due to the circular nature of the problem. So to summarize, we first gather all individual arrangements contributed by each bit type, and then we adjust for the total count of bits to ensure we are capturing the unique arrangement properly. Alright, checkpoint 5, input handling. Finally, in the main method, we handle the input. We read the number of test cases, and for each test case, we collect the bit counts in our list. This is straightforward but essential to set the stage for our solution to run correctly. So there you have it, a structured overview of the logic behind the bit ornaments problem. You have laid a solid foundation by breaking down the mathematical principles and the thought process involved in crafting the solution. Alright folks, let's wrap up. So today we tackled the bit ornament problem from HackerRank, where we computed the total number of ways to arrange colored bits on a string. We implemented a clever solution using modular exponentiation thanks to our custom ModPow function, which efficiently handles large numbers while keeping everything within the bounds. We also loop through the bits counting the bits count to calculate the total combination, showcasing how to manage lists and perform modular arithmetic effectively in C#. The big takeaway from this video: first, understanding the importance of modular arithmetic in competitive programming, especially when working with large inputs. Second, mastering the concept of exponentiation by squaring. It's a game changer for optimizing calculations. Make sure to check out the link in the description below if you have liked this video, and if you have found this content helpful, don't forget to give it a thumbs up and subscribe for more coding challenges and solutions. And stay tuned, because in our next video we'll dive deeper into dynamic programming techniques that can optimize even more complex problems like this. You don't want to miss it. Happy coding, and I'll see you next time.